Hi, welcome to the Piezo-Metrics channel. I'm Frank, and I'm here to demonstrate how to use Piezo-Metrics temperature compensation calculator. In a previous video, I went over the theory behind temperature compensation using a passive resistor network. If you would like to review the video, a link is given below. For the purposes of this demonstration, I will be using the data that I first used in our introductory video. If you would like to review that video, the link is given below. Before demonstrating the Temp Comp calculator, I would like to review the requirements for the gauge resistance data to draw your attention to what constitutes good gauge data, because if the data provided to the Temp Comp calculator is bad, the Temp Comp solution will also be bad. As we've seen before, here's a schematic of an open Wheatstone bridge comprised of strain gauges G1 to G4. The red and black lines are connected to the excitation voltage, and the green and white lines are for the bridge output. Here are the Temp Comp resistors RS, RZ1, RZ4, RB2, and RB3. These were previously discussed in another video. Recall that we only need some combination of RZ1 or RZ4 and RB2 or RB3 to compensate the bridge. As you may have noticed, I've included a shunt resistor, RP, to the bridge. This resistor allows us to calibrate the bridge output to a specific voltage at the full-scale load. I mentioned that inputting bad gauge resistance data into the Temp Comp calculator will generate a bad Temp Comp solution. So, what constitutes good gauge data? Here I show the gauge resistance data measured from an open bridge. It's comprised of 4 gauge resistance measurements made at 0 and full-scale load and at cold and hot temperatures. Now imagine that the strain gauges are bonded to a pressure diaphragm. Strain gauges G1 and G3 are bonded to the center of the diaphragm, and gauges G2 and G4 are bonded to the edges of the diaphragm. If the gauges have been properly bonded and the pressure and temperature conditions have been properly applied, we will see the following good gauge behavior. First, at 0 load, at the cold and hot temperatures, we'll see that all 4 resistances will be within 8% of the average resistance of the set. Second, we also see that the resistances at hot are greater than the resistances at cold, since our gauges have a positive TCR. Third, at the full-scale pressure and at the cold and hot temperatures, we'll see that the resistances of G1 and G3 will increase relative to the 0 pressure condition at both temperatures. We'll also see that at the full-scale pressure and at the cold and hot temperatures, that the resistances of G2 and G4 would decrease relative to the 0 pressure condition at both temperatures. If the gauge data do not follow this pattern, there may be a problem with either the bonding of the gauges, the accuracy of the experimental conditions, or the instrumentation used to measure the resistances. Once we're sure we have good gauge data, we can enter it into the Temp Comp calculator. But before we do that, I'd like to go through the data the Temp Comp calculator expects as input. In a previous video, I mentioned that the minimum amount of data was 4 gauge values for 2 load conditions and 2 temperatures. As you see here, we have added the requirement that the gauge resistances at ambient at 2 load conditions be applied. We recommend that the gauge data be measured at ambient to verify their function before a lot of time is spent temperature conditioning the sensor. We believe this is just good practice. With the addition of the ambient gauge measurements, the minimum number of data points now is 24. Here I show the full set of expected data for the Temp Comp calculator. It's comprised of 4 columns containing the gauge resistance data, and there's a 5th column that contains a sensor ID number which has a maximum of 6 digits. The user is free to choose an ID number. The first set of 2 rows contains the gauge data measured at the 0 and full-scale load at ambient. The second set of 2 rows contains the gauge data measured at the 0 and full-scale load at cold. And the third set of 2 rows contains the gauge data measured at the 0 and full-scale load at hot. Once the data has been collected, they should be saved in an Excel file with CSV formatting. Now that we have our data ready, we could go to the Piezo-Metrics website to access the calculator. We can click on the Services button and scroll down to the Temp Comp calculator and click on the link. The first page allows us to enter the source excitation and also the desired full-scale output. After that, we could click on this link to upload our data. And then after that, we could click on the Validate Input Data button. Since we have a pressure diaphragm, our data falls under the bending data category. As you can see, all our data is good. We also have an Axio data checker, and in this one, it will verify the Poisson strains. Now, if you have some indicators that show not okay, we have a series of recommendations here that you could look at to find the source of the problem in your data. Now we could click on the Calculate Temperature Compensation button. And here we have the solution. You could also click on the Export to PDF. And the PDF file contains all the results that were shown on the previous screens. To make it easier to look at the results, I've reproduced the TempComp solution here. We see that 4 passive resistors have been added to the Wheatstone bridge. There is now a shunt resistor RZ1 with a value of 35 kiloohms that is connected to gauge G1. There's a series resistor RB3 with a value of 11 ohms connected to gauge G3. There's a bridge series resistor RS with a value of 845 ohms and a bridge shunt resistor RP with a value of 1000 ohms. With this TempComp solution, we see that at 0 pressure, the predicted bridge output varies between 0.07 millivolts and 0.1 millivolts over the temperature range. And at full-scale pressure, the predicted bridge output is about 100 millivolts over the temperature range. In this video, I've gone over the data requirements for the TempComp calculator. It's important to keep in mind that the TempComp solution is only as good as the data that goes into it. As we've seen, the TempComp calculator first goes through a data verification step to identify any potential problems with the data. The data can always be submitted to the calculator, even with problems, just to see what kind of solution comes out. However, the solution is only as good as the data that was supplied. Piezo-Metrics is making this temperature compensation calculator freely available for everyone to use. To access this calculator to temperature compensate your sensor, please visit our website at the link given below.